All right, here's 2009, number 6. Letter C on here we're gonna skip over. It's a garbage question, so I'll look at it for a second, but I'm gonna mow through that one pretty quick. Don't stress about that one. So here we go. 2009 6A says consider 2 chemical species, sulfur and the sulfur ion there, sulfide. Write the electron configuration for each of those species. Make sure you have a periodic table next to you when you sit down to take the exam so that you don't panic here and not be able to see what you're doing electron configuration wise. So sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. That's what sulfur looks like. You get a point just like that for doing sulfur's electron configuration. And then the next part is a sulfide ion. What have we done here with the sulfide ion? We have gained 2 electrons, and so in the gaining of 2 electrons, the first part of this is all the same. 1s2, 2s2, 2p6, 3s2, and then instead of 3p4 we have a 3p6 here for the electron configuration on the sulfide ion. Easy enough. That's A.1. Then A.2 says explain why the radius of the sulfide ion is larger than the radius of the sulfur atom. What do they have in common? They're both sulfur, so the nuclear charge is the same. The fact that the sulfide ion has 2 additional electrons means it has greater repulsive forces and a larger radius. That's answer 6, part 2. Nuclear charge is the same, extra electrons, extra repulsive forces, larger electron cloud, larger radius. So that's the idea there on part 2. And then part 3 says which of the 2 species would be attracted to a magnetic field. Oh, this is a little blast from the past. Magnetism is controlled by whether or not the highest energy level has all paired electrons or has lone electrons. So the one that's attracted to the magnetic field is the one that has lone electrons and not all paired up electrons. So when we look at the 3p on the sulfur atom, it looks like this, and those 2 lone electrons there cause this to be magnetic. The sulfide ion is not capable of being magnetic because it has all paired up electrons, and so you've got to explain that in the words. So sulfide or the sulfur atom, sorry, is magnetic because not all the valence electrons are paired. Sulfide ions can't be magnetic because no unpaired electrons. And you can draw them up, that's fine. But you need to put it in a word expression. That's a long time ago we talked about that. In the D block elements, the ones that have lonely electrons like that, remember they have some kind of color to their salt. They have some kind of color in solution also. That's part A. That's a long part A. Then we get to part B, and part B talks isoelectronic. Isoelectronic means they have the same number of electrons. So it says sulfide ion here is isoelectronic with argon. From which species is it easier to remove an electron? They're talking about ionization energy, how much energy is required to remove an electron. So in B, if they're isoelectronic, same number of electrons, so I would write sulfide and argon have same number of electrons, but argon has a greater nuclear charge. It has 2 additional protons, so it has a greater nuclear charge, which makes the energy required to remove an electron greater. That bigger positive nuclear charge is holding on to those electrons a little tighter. That's part B. Part C, I said I'm going to scrap here. Part C, I think, is more confusing than helpful. It says H2S molecule has a bond angle close to 90. I've kind of told you, we talked about this with water, and H2S looks exactly the same as far as the structure goes. If we were drawing it with water, that bond angle is roughly 104.5 degrees. If we had 4 domains and all things bonded, we're at 109.5. Those lone pairs cause that that hydrogen angle to be squeezed down a little bit to 104.5. H2F, it's telling us, we don't get to argue with what they say. It says the bond angle is close to 90. It's about 92 degrees. I looked it up a second ago. So that's real information. On the basis of this information, which atomic orbitals in the s atom are involved in the bonding with the hydrogen atoms? I dislike this because it's hybridized. And so when it's hybridized, those S's and P's and the sp3 hybridization, they spread as far apart as they can. This wants you to say that because the p orbitals are x, y, and z orbitals like this, that those guys would be 90 degrees apart, and so the atomic orbitals involved are the p orbitals. I just find it to be a poorly written question, and so don't stress about C there. I would much prefer you understand the hybridization looks like that, and the hybridization pushes those things so that they are all 109.5 degrees apart, and then those lone pairs manipulate that a little bit. In this case, you've got, when you go from H2O to H2S, sulfur's a bigger atom, and so those lone pairs push the hydrogens a little closer to each other, and you get that 92 degree bond angle. But their explanation for you saying that that's p orbitals involved, I think is poorly done. Part D. 2 types of intermolecular forces present in liquid H2S are London dispersion and dipole forces. Compare the strength of London dispersion forces in H2S to the strength of dispersion forces in water. Dispersion forces are all based on the number of electrons. So H2S has bigger dispersion forces than water because H2S has more electrons and greater, you can put polarizability there, polarizability. Polarizability is a dispersion force thing. think that's D part 1. And then D part 2 says compare the strength of the dipole forces in H2S to the strength of the dipole forces in water. Now we know water has hydrogen bonding. That's a specific type of dipole force. So the dipole forces on D2, dipole forces in water are stronger than H2S. Why? This is about polarity of the molecule, right? Oxygen is way more electronegative than sulfur, so it's pulling harder on those electrons. So the reason the dipole forces are stronger because oxygen is more electronegative than sulfur, and therefore attracts electrons more. Yeah, you probably should put attracts shared electrons more and causes greater polarity. And that's it on D2. That's 2009, number 6. It's not too bad. I think there's a lot of good conceptual stuff in there. You can go back and look over.